Welcome back to Fundamental Theorem of Calculus, Part 2. It's the sequel. It's the remix. We're going to talk about the second part of the fundamental theorem, which is much less algebra heavy and just more conceptual. So what happens when you take the derivative of an integral of a function? So there's your notation. Remember that an integral has to have a dx on the end of it. So all of this says to integrate it. Remember that d dx means take the derivative with respect to x, and then there's no y up there because you're differentiating. So I kind of hope you already know this answer, maybe even if you're too scared to think that you know it. But if you take the derivative of an integral, you get your function right back. That's the fundamental theorem of calculus. It's actually the first part. I did them out of order because I like it better, but there you go. Okay, but there are some nuances here, and they all have to do with notation because the order in which you do these things can matter. So let's talk about what would happen if I took the derivative of an integral. I'm going to put a function in here now, like something terrifying. The inverse sine. Do you know how to integrate inverse sine? Nope, you sure don't, but you don't need to. So order of operations says you would work inside out. So the first thing you would do is you would take this integral. Remember that when you take these integrals, you would anti-differentiate and you'd have a plus c on the end. But then you would go take its derivative. And so you would get back out just inverse sine. Okay, that's nothing crazy. But what if I switch the order? What if I ask you to integrate the derivative of inverse sine? So this is all take the derivative, and then this notation on the outsides are for your integral. So that's the order you would be doing it in. This question you could actually do because you know how to differentiate anything. And then if you're just anti-differentiating it back, it's just going to undo itself. But the nuance here, like the context, but the nuance here is in the notation because of the order you're doing it in. So if I differentiate inverse sine, I get something. If I come right back and anti-differentiate it, I'm going to undo it. But the last thing I did was take this thing called an indefinite integral with no bounds on it. You need a plus c. That's the difference between the first one we did here and this second one. The order in which you do these things matters. So read them inside out. Okay, what if I take the integral from 2 to 95 of the derivative of, I'm not clever enough today to come up with stuff. It doesn't matter. Okay, so think about the order that you're going to do things in. You would take this derivative first. It would be super fun. You could do it. Then you would come right back and anti-differentiate it. Now remember what we did yesterday with the bounds. So I would take its antiderivative and I would get the function right back, but I would have to evaluate it from 2 to 95. So this one would be the cosine inverse of 95 minus the inverse cosine of 2. And that's a quick little nuance for that. So the last one left to do is if I, what order? Differentiate the integral from 2 to 95 of inverse cosine. Okay, so remember your order. You would take the integral first, and then just like yesterday, you would have that integral, whatever it is, and you would evaluate that integral between 2 and 95. Like plug in 95 and then plug in 2. And when you're done with that, you get a number, like you get a constant out because 2 and 95 are both constants. You're going to plug them in. So if the very last thing you do is take the derivative of a constant, you're going to get 0. All right, so all four of these situations are the same thing, but the order matters. The order that you do these things in matters. Okay, so one more variation. What if I differentiate the integral from 2 to x, some function? Now you're going to panic for a second, and that's okay. I'll let you have your moment of panic. Don't worry that there's a t. It doesn't mean anything. There is a rule in calculus that you cannot use the same variable in your bound that you use in this thing here called your integrand. So, okay, we'll follow the rules and we'll just pick a different letter, and that's okay. Okay, this one we're actually going to work out because I need you to see everything that's happening. So we're going to go take this integral. That's why I made it so pleasant. We're going to take this integral. All right, so if I add 1, divide by the new, cancels the coefficient, and then I'm going to evaluate from 2 to x. All right, so this is just the integral portion of it. Evaluating from 2 to x means I'm going to replace my variable t with my variable x, and then I'm going to replace my variable t with a 2. I know that's 8. You know that's 8. It doesn't matter. I'm going to leave it because I'm not done. Like, I still have this derivative to take, so I'm going to throw that here, and I'm going to throw that here. Okay, well, so let's go take that derivative. When I take the derivative, I pull the power, I subtract 1. When I take the derivative of a constant, it's 0, and I'm done. So my goal for you is to go from here directly to here, noting that it's the same thing we were talking about up here, how differentiating an integral makes it go away. You just have your bounds to deal with. So let's see if we can come up with some patterns for these bounds. So what if I ask you to go here? I'm just going to write it this way. Take the derivative with respect to x of, and I'll just give you a bunch of different ones. So what if we have the integral from x to 6 of t to the 9th? Okay, well, let's go through this one again. I'd have to add 1. I'd have to divide by the new. I'd have to evaluate from x to 6. That would give me 6 to the 10th over 10 minus x to the 10th over 10. But remember, the instructions are to take the derivative. So if I go differentiate that, if I go d dx it, 6 to the 10 over 10, then I would have 0 minus, pull a power, subtract 1. Sorry, that was supposed to be an x to the 9th. Okay, so this one's different because the bounds are in different order. So I'd go directly from here to negative x to the 9th. One more, maybe more than one more. What if I have the integral from 2 to x to the 4th, like something weird? How about sine? There, that's a good idea. I'm so smart. All right, what do you differentiate that gives you sine? Negative cosine. So if I get negative cosine of t from 2 to x to the 4th, and then I plug in, I'd have negative cosine of x to the 4th minus negative makes it a plus cosine of 2. And then when I go take that derivative with respect to x, like the instructions tell me to do, this is very different. So when I take a derivative, now I have a chain rule to consider, friends. Remember chain rule? It's still a thing. So the derivative of negative of negative cosine is sine. I get the x to the 4th, just like I thought I would, times the derivative of what I plug in is a 4x cubed. This derivative is 0 because it's a constant again, so I'm not even going to worry about it. Again, my goal is that you go from here directly to here. That's not a goal. Like, that's a necessity because they're going to put things inside these integrals that you can't do. I'm putting friendly things in here so that we can hopefully start to get a pattern, but they'll put things in that you can't do. So let me write the pattern. You're differentiating an integral, which means you get it right back, just like we talked about at the beginning of the video. And then when you plug in your bounds, just like you've been doing for 3 days straight, and you plug in top minus bottom, you have to remember to take the derivative of your bound. So if I write this in like notation, if I make this like an x to the sixth and I make this a sine of x, and then I make my function something disgusting that you can't integrate, like, I don't feel like being very disgusting. Here, I don't feel like it. I'm not gonna, because you could do that. But if I give you that, you need to be able to immediately say, okay, differentiating an integral gives it right back, but I'm going to plug in top minus bottom. Oh, but I have a chain rule to consider in each term. So now this one also gets multiplied by a cosine, and this one also gets multiplied by 6x to the fifth. So you plug in top, you plug in bottom, times derivative of what you plug in. That's your chain rule. These are the ones they're going to put on the AP test. These are them, and they're going to give you answer choices without these chain rules in them. And you're not going to pick those because you know better, don't you? We'll practice more. See you soon.